So there's two that come to mind, and the first one we've talked about a bit before, but that's data quality. So if your images are noisy, if they're full of artifacts, if there's a problem with your labeling, if the annotators had instructions but they interpreted it different ways, that's going to be a challenge in getting the model to learn these different perspectives. So anything related to data quality, image quality, label quality is kind of the first one. But there are some things you can do to prevent that. You can carefully plan how you're going to acquire these images, carefully check the quality of them. Maybe you need an additional automated step that does quality checking and discards images that don't meet your standards and can't be processed by the computer vision. You need a standard process for annotation. So you might take a first pass at this is what the annotators are going to do, but then you have a few of them go through it and you discover that they interpret it in different ways. So you need to go back and iterate on your annotation instructions and repeat that until you have a consistent set of annotations. So any kind of standardization there can help. And iterating quickly in order to get that information. So don't annotate your whole data sets. Don't collect all your images. Take a small sample, train your baseline model, see what you learn, and go back and try again if there's mistakes in it. So anything related to data quality is kind of number one. The other one I don't think we've talked about as much, and that's overfitting. And what I mean by that is a model that performs well on your training data, but fails on real world examples. So that could be because your training data is not diverse enough. It could be because there's a distribution shift. For example, you're at inference time, you got images from a different imaging device, different scanner, different camera, different lab, something changed there, or they're from a different part of the world, or they're patients of a different race, different age, different sex, anything like that that changes, your model can very easily fail. And if you're naive going into it, those types of problems do come up. You need to understand the data. You need to work with domain experts in order to understand it. They're the ones who understand the distribution shifts far better than any of us technical people. As a machine learning engineer, we know it's a problem, but we don't know what those shifts are that we're trying to guard against. Domain experts are critical there. We need to plan for a diverse training set, plan for proper validation so that we can catch this before deploying the system. So that could be collecting data from a different facility, different part of the world. It just depends on the problem as to what that means. But the key is to be able to catch the problem before deployments. So those two of data quality and overfitting to me are the main two that come up.
Definitely. I feel like, yeah, data is number one for me as well. Yeah, overfitting, it can be very challenging, especially when you work with a small amount of data. The more data you have, in general, I would say that it's less of a problem. Then I would say like misaligned objectives, like when the internal metric that you have uh, as a as a data scientist, it's very different from the one that your customer actually cares about. That I've always feel that this is a big problem as well. Um, I mean, the other one would be edge cases. I feel it ties a little bit with overfitting because uh, yeah, is what we are talking. If there is none of those edge cases on your training set, then when you're trying it with real world data, then it might contain those edge cases that they have not been taken into account. So there's quite a few to take into account, but that's why it takes a little while to learn about computer vision and understand what are the important points in order to have a successful project.